The Birth of Zero, the chapter you're waiting for about base 10. Now 0 may not be very significant, but it is very important. Next time someone calls you a 0, just think of yourself as really important. If you were a 0 in a number system, you would be the placeholder. You would be the person that moves those digits to the left and makes them more significant. The number 100 has 2 zeros in it. It only has a 1, but the 1 is positioned in the 100 column. It's because those 2 zeros are there pushing that 1 to the left. As a 0, you would serve as a divider, the perfect center between negative numbers and positive numbers. So not only are you a placeholder, but you're the center of the number line. You can thank the Mayans for the 0. Because early positional or column-based number systems, they extended tally marks. They were done by Greeks, Egyptians, and Hebrews. The Babylonians, the Chinese, the Aztecs, they done their independent work too. But the person that really tied it all together and put the bow on the box, Aryabhata. Because around 1498 AD, he developed a place-to-place system where each column was 10 times the previous value. And this is the origin of our decimal-based number system. He was also a famous astronomer. He calculated pi. He found the radius of the Earth with less than 1% error. He was born and died in India from 1476 to 550. So let's take our number 123, 123 that we're familiar with. And why is it 123? It's because the 1 is in the hundreds column. So it's 1 times 100 plus 2 times 10, because 2 is in the tens column, and 3 is in the ones column or units column. And when you add those up, 100 plus 20 plus 3, you get 123. But what's really more important is not that they're a 1, a 10, and a hundreds column. First of all, position does matter. The numbers to the left have more significance than the columns or digits to the right. And the proper way to think of those columns is really the base raised to the 0 power. So on the right side, we have 10 to the 0. And any non-zero number raised to the 0 power is going to equal 1. So 10 to the 0 gives us a 1 column. 10 to the first power is just 10. And 10 squared, of course, is 100. And if we keep moving to the left, we would have 10 to the third for 1,000, and so on. So as a little side note here, any non-zero number raised to the 0 power is equal to 1, as we just seen. Express that in programming form. It's been discussed since the 1700s. What if you raise 0 to the 0 power? Well, some obvious choices would be 1, 0, or undefined. Well, the mathematicians have defined it as undefined, and that is their final answer. Since you cannot divide 0 by 0, that's also undefined. It sort of makes sense that 0 to the 0 power, if you take nothing and raise it to the nothing power, you would think it's 0, but it's not. It's actually undefined. Now, who was Euler? Well, he was a Swiss mathematician that lived in the 1700s, and he founded much of the number theory and graphing and things like that. So it's a little off-road here, as you see by the icon, but it's someone you should know. If you're going to read any interesting books, there are many books written about the number 0 and, of course, Euler. So the anatomy of our base 10 number system, each column uses a single digit, a glyph, or a symbol, and we know what these symbols are. There are 10 symbols, the same as the base. In base 10, we have 10 symbols, 0 through 9. We cannot put a 1 and a 0 in a column, because to represent 10, we put 1 in the tens column. It's like having reusable parts. In fact, it's exactly like having reusable parts. In our Roman numeral system, they are always searching for the next glyph, the next symbol to represent the next highest digit. We don't have to do that. We have 10 nice symbols that we can use to represent any number, no matter how high, how small, or how negative, or how positive. Now here's what's interesting too. We have a decimal point. The numbers to the left of the decimal point, as we've seen, are 1, 10, 100, 1000. The numbers to the right of the decimal point is like 10 raised to the negative 1, or the reciprocal of 1 over 10 to the first, or the reciprocal of 1 over 10 squared. So 10 raised to the negative 2 is 1/100th. 10 raised to the negative 3 is 1,000th. And 10 raised to the negative 4 is 1/10,000th. So we can have an infinite number of digits to the right of a decimal point and an infinite amount of digits to the left of a decimal point. The interesting thing is the leading zeros to the left of the decimal point don't matter. Just like that decimal point is a center mirror that reflects the fractions and the whole numbers, the zero on the far right of the decimal point doesn't matter. So 1.2 or 1.20 or 1.2000 is all the same because we're not adding any more 1/10,000ths or 1/100ths or whatever column those zeros are in, just like the zeros on the left side don't matter. So we can see there's valid decimal numbers. You can have a single digit. If you were writing a parser in a language, you could look for a single digit and that would be a valid number. Or you could have an optional plus sign in front of it, which is the same as not having the plus sign. Or you could have a leading zero in front of it, maybe to just fill in spaces or columns in a spreadsheet or to make your numbers line up. 0, 1 is the same as 1.0, 1.0, 1 point, and plus 1, just like 12 and 0012 and plus 012. The last thing we see is the negative 0 with the blue zeros, 1, 2.5, and the blue 0 on the end. The zeros on the right are optional, the zeros on the left are optional, and that's what makes up the anatomy of a base 10 number. But there's two more things, and that's the comma. $1 million is much easier to read with 2 commas in it because it groups our digits in thousands or in threes. So every 3 you can optionally put a comma in there just for cosmetics. And then we have repeating decimal. Some of the numbers cannot be expressed perfectly, like 1/3 or 3 divided by 11 is 0.27, 0.27, 0.27. It goes on forever. Well, we can write that as 0.27 with a bar over the 27, showing that the 27 repeats, or we can write 0.27 with 3 dots after the 27, showing that it's a repeating pair of digits, as you see on the bottom. You would think base 10 is perfect and no one's going to complain because practically the whole world uses it. No matter what language you speak, everyone understands the number system because we all use the same digits and we all understand what they mean. But there is a movement that started in 1944 and it continued on in 1959 in the UK, and you can go to the website. There is a base 12 movement. The dozenal.org website will tell you more about that. A little crazy, but it's there. What are the advantages of base 10? Well, first of all, it has a 0. It has no positive limit. You can count to infinity. It has no negative limit. You can count to negative infinity. And it's very nicely designed symmetrically around the decimal point and the 0. What works on one side works on the other side. So you would think that there's no disadvantages. You cannot represent fractions without repeating decimal digits if that's a slight disadvantage. But really, it's not computer friendly. And what you'll find out is why we need a base 2 system, because base 10 doesn't just fall into place with the bits.